Hey, welcome back. Here we are with our next lesson in geometry, a lesson on line segments. And let's begin by defining what a line segment is to open up. A line segment is part of a line consisting of two endpoints and all points in between. Now, it's very interesting. This definition is nothing at all like how Euclid would have defined line segment. First of all, he wouldn't have used the word segment. Euclid would have actually just called a line segment, as defined here, a line, or a right line to indicate that it would have to be straight. Because remember, to Euclid, all figures had to be drawable. So if you were drawing a line in the sand with a stick, all of his lines that he drew would have a beginning point and an end point. They wouldn't just continue on forever. To us in the modern day, we visualize lines as continuing forever in either direction at the end of the line. Also, we say that a line segment consists of all points between two endpoints. That's another thing that Euclid never would have said. When Euclid was doing geometry, he wouldn't have considered, as he was dragging a stick across the sand, that he was just adding a bunch of infinitesimally small points to the line all the way from one place to another. But that is something we do when we conceive of geometric figures these days, is we consider the points that they're made up of. Okay, so that's what a line segment is. Let's talk about what endpoints are, and then we'll get a picture of a line segment. Endpoints are the points at either end of a line segment. That makes sense. Okay, so the previous definition didn't name what endpoints are. Now we know endpoints are at either end of a line segment. Let's take a look at a line segment. Oh, wait a second. That's a line segment. I think I need to fire my graphics guy here. Okay, so let's grab this line, this actual line segment here, okay? Now, actually, what's pictured here is not a line segment. This is a line. Notice that on either end, I have arrows showing that this extends infinitely in either direction. To make it a line segment, I need to get rid of the arrowheads and just have two end points. Now A and B are endpoints, points at the end of a line segment. And then you can see that there's a whole bunch of points, an infinite number of points in between my two endpoints, A and B. This would be an example of a line segment. And then a line segment is named by its two endpoints with a straight line drawn over them. Now we've seen naming of lines that look like this. This would be the naming of line AB, but not line segment AB. To change this to a line segment, I would need to delete this double arrow over the top, and now I have line segment AB. And just to note, it's the same to name it this way as it would be to name it this way. BA and AB, it doesn't matter what order I name the endpoints. The key is, though, that a line segment has to be named by its endpoints, by the points that are actually on the end of each line. Okay, so let's continue. We're going to talk about the word congruent next, and then we're going to talk about congruency in connection with line segments. Two geometric objects are congruent if they have the exact same size and shape. With line segments, this is easy because line segments don't really have a shape other than that they're a line segment. They're a one-dimensional object with two endpoints. Okay, so I don't have to worry about like the shape of a line segment when considering congruency. Congruent segments are simply, it's enough that they are both line segments. And as long as they have the same length, they're congruent. What is length? Well, actually, interestingly, our Saxon math book highlights length as a term that you should know, but it never defines it. So I actually had to go to the dictionary to look up the definition of length. It's a measurement from end to end of the extent of something. That's a great definition. The only other thing I'd add to that definition, it has to be measured in some kind of units. Okay, so we're actually using some measuring tool to identify what the extent of something is from end to end. And as we use that measuring tool is going to be measuring in a certain number of units. Now, let's take a look at another line segment here. Nope, that's a line segment. Line segment. Okay, there we go. So, CD is another line segment. I would call it segment CD. And let's say that I measured AB with some measurement instrument and found that it had a length of 3. And I measured CD and found that it had a length of 3. If I found that these two segments had the same length, I would say that segment AB is congruent to segment CD. That is a congruence statement, a statement that two figures are congruent. In this case, my figures are line segments. And I'm just going to identify what that looks like. This is a congruence statement. Notice I say segment AB. Then I have the symbol for is congruent to. The congruency symbol is an equal sign with a little squiggle symbol over the top. And then CD, segment CD. So here I'm saying segment AB is congruent to segment CD. Why are they congruent? Well, the only thing required for congruency of line segments is that they have the same length. All right, and then just lastly, one other way to demonstrate congruence without a congruence statement is to use tick marks. Tick marks are small identical marks, and where you see those identical marks, you know that the segments are congruent. I have some tick marks over here that I'm just going to drag into the picture. If I had these tick marks laid on top of my figures, they're identical marks. I didn't do a great job centering them. Let's see if I can get this top one a little bit better here. But they're identical marks, okay? And what they're meant to do, since this has a single tick mark and this has a single tick mark, I know that these two segments are congruent to one another. If one segment had a double tick mark and one had just a single tick mark, so one had two little lines and one had one, I know they weren't congruent, or at least I don't have any evidence that they're congruent. But if they both have two tick marks, that means that they are congruent. Okay, so that's how tick marks work as another way of demonstrating congruence. And then finally, since we're talking about congruence, let's talk about some properties of congruence. There's 3 properties of congruence you need to know. We're going to be using these later this year in proofs, so these are going to be coming back. They're going to seem pretty self-obvious though, I think. Here's the first one. The reflexive property of congruence states that any line segment is congruent to itself. Why is a line segment congruent to itself? Well, a line segment is always going to have the same measure as itself, and I guess technically the same shape as itself, but we're not really concerned with shape of line segments because they're all the same shape. So the reflexive property of congruence is that line segment AB is congruent to line segment AB. What about the symmetric property of congruence? Well, this says that if AB is congruent to CD, then segment CD has to be congruent to segment AB. Once again, if we think about measures, this makes a lot of sense. Up above, I have AB and CD have the same measure, 3. If AB has a measure of 3 and CD has a measure of 3, they must be congruent. That means that CD has a measure of 3, and so does AB. It has a measure of 3, so CD and AB must be congruent. I can say it either way, and it's true. So this is another one. It's pretty self-evident. Just know that this is the symmetric property of congruence. The last one is the most complicated, but not too difficult to understand. If AB is congruent to CD and CD is congruent to EF, wait a second. Let's just think what this means here. That means that like if AB has a length of 3, right? And let's say that CD also has a length of 3. Because they have to, in order to be congruent, they'd have to have the same length. So CD has a length of 3 still. And then another segment is congruent to CD. It must have a length that's the same, a length of 3. Well then, AB must be congruent to, oh, I'm sorry, this is incorrect. It should be AB is congruent to EF. But it should still make sense because AB had a length of 3 and EF has to have a length of 3, so they still have to have the same length. So if AB is congruent to CD and CD is congruent to EF, one segment's congruent to another, that second segment is congruent to a third, then the first segment has to be congruent to the third segment. That's the transitive property of congruence. All right, we're going to move on to some more topics in the line segments chapter in the next video.